Okay. Hello everyone, it's Salar and we are in part 54 of tutorial. This tutorial, a tutorial to writing a real-time operating system. In previous part, I described the concept of semaphore and locking mechanism. Okay? And I said, when you want to share a resource between two threads or more than two threads, to prevent conflict, you must use locking mechanisms like semaphore. Okay, and in previous part, in the end of previous part, I said in this part I want to implement the semaphore. So let's implement the semaphore in the RTOS. If you see the repository of project in commit number 12, I've implemented and added semaphore to the RTOS under this commit, initial addition of RTOS. Okay, but let's inspect this implementation. First, if you want to have semaphore in the RTOS, you need to have semaphore control block like thread control block, and in semaphore control block you have some information about a semaphore like thread control block. Okay, each semaphore has ID like thread. This ID is the address of semaphore control block in memory. Each semaphore has a name, it's a string. Each semaphore has a count. In previous part I said what's count: number of free resources. Okay, each semaphore has a maximum count, maximum number of resources, and initial count. Okay, when the RTOS creates semaphore, put this value in creation. In creation of semaphore, put initial count in count. Okay, and semaphore waitlist. I said in previous part, when a thread wants to get a semaphore but the count of semaphore is 0, RTOS put the thread in waitlist and put thread in semaphore waitlist according to the priority of thread. And semaphore waitlist is a binary tree. Okay, it's a binary tree and is an ordered tree. And when a thread wants to release a semaphore, if the count of semaphore is 0, RTOS return most prior thread from this data structure to the ready list. Okay, and get semaphore for most prior thread. So to support semaphore, we need to have semaphore waitlist. And like other data structures in the RTOS, semaphore waitlist implemented in list.h and list.c. Here in Untitled project RTOS include list.h. I've defined semaphore waitlist manipulation functions. Semaphore wait node is a binary tree node, and semaphore waitlist is a binary tree. You can create a node, semaphore wait node, create a list. If you see the implementation, creating a list is creating a binary tree. Okay, you can insert a thread to a semaphore waitlist, delete a thread from a semaphore waitlist. You can get minimum thread, list prior thread. For example, here minimum here is the thread. For example, assume here is thread 1, thread 2, thread 3, thread 4. Minimum is thread 3 because has the lowest priority in this list. Get max is most prior thread in the list, is T1. Get size and check is empty or not. Okay, and implementation is in list.c, and implementation is straightforward, and you can study the implementation by yourself. Okay, so to implement Semaphore, we need to have Semaphore WaitList and Semaphore WaitList data structure defined in list.h and implemented in list.c. After that, if you want to support Semaphore, each thread must have a Semaphore wait node. When you want to insert a thread in this list, each thread must have a node. Okay, Semaphore wait node. And you need to add another member. This member is Semaphore waiting for. For example, assume this list is Semaphore 1 Semaphore waitlist. Okay, assume this data structure is Semaphore 1 waitlist. Okay, thread 1 now waited for Semaphore 1. Okay, thread 1 at this time, thread 1 waited for Semaphore 1. You must write the ID of Semaphore 1 in thread 1 control block in this member, and you must add another member returned by release. I will get into this member in next parts. Okay, so you must add these members in Semaphore in thread control block here, in thread control block here, Semaphore waiting for, Semaphore wait node, and return by release. And you must initialize these values when you create a node, create a thread. When you create a thread, in thread create news, you must initialize Semaphore wait node. Okay, create a node, you must initialize Semaphore waiting for to null, because when you create a thread has not waited for a semaphore, and you must initialize this value to 0. Okay, I will get into this member in a few slides ahead. Okay, a few slides ahead. And these are Semaphore system calls. For each semaphore, for Semaphore, you have semaphoreGet name, a getter system call like thread get name. To create a semaphore, you must use this system call, thread create new, needs a name. The system call needs a name, a max count, and an initial count. Okay, to delete a semaphore, you can use this system call, delete this semaphore, and get and release. I described these two system calls in previous parts. But if you want to add a new system call to the RTOS, first in system call type definitions in this header file, you must allocate a system call number for each system call. Okay, you must define a specific structures for each system call, to send arguments to kernel. okay, like threads. And you must have kernel space system calls, okay. And in RTOS.h, this is the definition of user space system calls, okay. And in Semaphore.c, all of system calls implemented in Semaphore.c, okay. Like adding a new system call to thread. If you want to add a new system call, for example for Semaphore, you must do these works. But first, let's talk about Semaphore create new. Study Semaphore get name by yourself. It's a simple system call, okay. But Semaphore create new. To create a new semaphore, you must initialize semaphore control block. Here is implementation of Semaphore create new. First, put all of arguments in a specific system call. After that, put address of this specific structure to the global structure in addition of a system call number, okay, and call kernel system call. And in Semaphore create new system call, kernel space system call. First, allocate memory for Semaphore control block. Put this address in Semaphore ID, initialize the name of Semaphore, initialize Semaphore count by Semaphore initial count, this argument initial count, okay. Semaphore max count by max count and initial count by initial count. Create Semaphore WaitList, a binary tree, okay. And Semaphore has been created. At this point, Semaphore has been created. It's so easy, okay. And you can't call Semaphore create new from interrupt, okay. If you call Semaphore create new from interrupt, this function return null value, otherwise return the ID of Semaphore, okay. It's so easy. After that, Semaphore delete. Let's inspect this system call. Before deleting a semaphore and returning memory to the system, you must do this work. Before deleting a semaphore, RTOS must return all of its weighted thread to the ready list. When you have a semaphore, there may be some threads in this data structure that waited for semaphore. When you want to delete a semaphore, you must return all of these threads to the ready list, okay. Delete them from Semaphore WaitList. After that, delete them from WaitList, kernel WaitList, and return them to ready list, because there is no semaphore to wait for that, okay, anymore, okay. Semaphore has been deleted. So for semaphore delete, like before, send its argument to kernel by using of these structures. You can't call semaphore delete from interrupt. And in kernel space system call, check semaphore WaitList size. If size is greater than 0, this means some threads have waited for semaphore. and in this for block for statement, you must delete all of semaphores. First, delete them from semaphore wait list. Okay, get max from most prior thread. You must delete them from most prior thread. Get max, delete it from semaphore wait list. Delete from semaphore wait list. Change semaphore waiting for in thread control block to null, because at this time the thread has not waited for semaphore. Okay, because semaphore has been deleted. And delete the thread from kernel wait list and insert it to ready list. Okay, delete from wait list, delete from kernel wait list, and insert it to ready list from most prior thread, and after that next most prior thread. Okay, so when you want to delete a semaphore, before deleting a semaphore, RTOS must return all of its waited thread to the ready list. Now let's inspect semaphoreGet system call. This figure, this chart shows the implementation of SemaphhoreGet. SemaphhoreGet implemented according to this chart. Now let's start from here. When a thread wants to get a semaphore, if the count is greater than 0, if count is greater than 0, this means there are at least one free resource. So RTOS must get the semaphore for that thread. Okay. Here is implementation of user space SemaphhoreGet, but I will talk about this part in next slides. Okay, I will talk about this part of code in next slide. But like other system calls, you must send arguments to the kernel. Arguments in addition of semaphore caller. Semaphore caller is the thread that's called the semaphore. Okay, in kernel space system call, you need this value, caller of semaphore, and its current running thread. Okay, by using of kernel get current running thread, you can acquire the caller of semaphore. And in this version, you can just call SemaphhoreGet from thread. You can't call this system call from interrupt. Okay, when you call from thread, you can get the caller by using of kernel get current running thread ID. You must send these values, this information to the kernel by using of kernel system call. But in kernel space, if the count is greater than 0, do semaphore count minus minus and return OK. Everything is OK. Okay? Otherwise, if the count is 0, this means there is no free resource. If the timeout, the delay value equal to 0, return error and immediately return from SemaphhoreGet. Otherwise, if timeout is greater than 0, put semaphore to the wait list. Let's inspect the code. If timeout is 0, delay is 0, return from semaphoreGet and return its value. Status error resource. Otherwise, if timeout is greater than 0, first put the color of semaphore to the wait list. Put semaphore color to the wait list. And now semaphore color waiting for the semaphore. Change this value in thread control block of semaphore color, this thread. Okay? After that, delete semaphore from ready list and insert it to the wait list according to the timeout. Timeout is a delay plus current tick is a return tick, and like before, you can acquire wait list number by using up this formula, return tick modulated by number of wait list, like putting a thread in a wait list in thread wait system call. Okay, after that, if context switch is necessary, do context switch, but I will describe this line and this line in next slides. Okay, in next slides. So when a thread wants to get a semaphore if count greater than 0, get it. If count is 0 and timeout is 0, return error. Otherwise, put thread in the wait list and wait for semaphore until to the end of this delay. Now let's describe semaphore release. Semaphore release. When a thread wants to release a semaphore, when the count is greater than 0, this means there is no thread in this data structure in semaphore wait list. Okay, and you can easily do count plus plus. Okay, let's inspect the semaphore wait list. Here is semaphore wait list. In this version, you can't call semaphore release from interrupt, but in future I will implement this part, and I will implement calling semaphore release from interrupt. Okay, I will implement calling semaphore release from interrupt, but in this version, if you call semaphore release from interrupt, this function, this system call return this error, status error interrupt. Okay, but you can call this system call from thread space. Okay, like before, put the argument in specific structure and call kernel system call by using a global data structure. Okay, and in semaphore release, if semaphore equal to 0, else if semaphore is greater than 0, semaphore count plus plus. But if the count of semaphore is max count, you can't increase the value of semaphore, the count of semaphore. Okay, otherwise you can do semaphore count plus plus. Okay, if semaphore count is greater than 0, do count plus plus. Otherwise, if count equal to 0, when the count equals 0, there may be some threads in this data structure. Okay, there may be, and you must check the size of semaphore wait list. If no thread waited for semaphore and list is empty, size is 0, just do count plus plus. If the count of semaphore is 0 and list is empty, semaphore wait list is empty, do count plus plus. and write 1 in semaphore count, because semaphore is 0, semaphore count plus plus is 1. Okay. Otherwise, if size of semaphore waitlist is greater than 0, this means some threads waited for the semaphore, and you must, and RTOS must, return most prior thread and get semaphore for that thread. Okay, return most prior thread from semaphore waitlist. Get max from semaphore waitlist. Get most prior thread. Okay, delete the thread from semaphore waitlist, change semaphore waiting for in thread control block to null, because since from thread has not waited for semaphore. After that, delete thread from waitlist, kernel waitlist, and insert the thread to the ready list, and change the state of thread to ready, and set returned by release in thread control block. Put 1 in this member. Okay, and return a status OK. And if context switch is necessary, do context switch, request context switch. But let's talk about this member. Returned by release, a member in thread control block. In semaphoreGet, here, in semaphoreGet, when a thread wants to get a semaphore, at put to waitlist stage, at this stage, when semaphore count is 0 and timeout is greater than 0, and RTOS wants to put the thread in the waitlist. It's not specified yet, will thread be able to get a semaphore or not? Okay, to inspect this sentence, let's see this slide. Let's see an example in this slide. Assume thread 1 wants to get the semaphore. Okay, assume thread 1 wants to get the semaphore, but semaphore count is 0. Semaphore count is 0. Okay, and RTOS puts it to the waitlist, and timeout is greater than 0, and RTOS put thread 1 to waitlist and semaphore waitlist. Okay, so after putting semaphore to the waitlist, there will be two situations. Assume timeout, for example, equal to 500 milliseconds. If before running out of timeout, if before elapsing this timeout, for example, after 100 milliseconds, another thread releases the semaphore, and in semaphore waitlist of that semaphore, thread 1 was most prior thread. In this situation, thread 1 will be able to get the semaphore, and the return value of semaphoreGet will be OK. Otherwise, if no other threads release the semaphore, thread 1 will not be able to acquire the semaphore. Okay, in this situation, waitlist handler return thread to the ready list after elapsing this delay, and thread will not be able to get the semaphore. So after this part there will be two situations. First, another thread released the semaphore, and thread 1 was the most prior thread in the semaphore waitlist. In this way, thread 1 will be able to get semaphore. Otherwise, thread 1 will not be able to get the semaphore. Now we use return by release this member to show which of this situation were happened. Okay, which of this situation happened. Returned by release. Before to reading this slide, let's to see semaphore release here. For example, assume thread 1 puts to the waitlist, has been put to the waitlist, okay? And now semaphore release wants to release a semaphore that thread 1 waiting for. If semaphore release by using of get max return thread 1 to the ready list, at this line put return by value set number 1 in this member of thread 1. Okay, in this member of thread 1 you can see in semaphoreGet this value initialized to 0 for thread 1. For example, for thread 1, when RTOS wants to insert thread 1 to the waitlist, this value has been unset. And return value is status wait. It's not OK or error, because at this time it's not specified yet. Thread 1 will be able to get semaphore or not. So semaphoreGet unset this value, and set the return value to status wait. Now, after returning to user space system call of semaphoreGet, after returning from waitlist, if semaphore list, if return by semaphore in for semaphore color has been set, this means, and this shows the thread return to semaphore return to ready list by using of semaphore release, because this value has been set. Okay, for example, for thread 1, if this value has been set and return value is status wait, return value was status wait, this means getting the semaphore was successful. Otherwise, if this value has not been set, the value is 0, this means semaphore color return was returned to the ready list by using of kernel waitlist handler. And at this time, getting semaphore was not successful, and getting the semaphore is unsuccessful. And semaphoreGet return a status error timeout. This means until to the timeout, no other threads release the semaphore. Okay, so if this value was 1, okay, return by release will be used to show thread which return to the ready list by semaphore release has been succeeded to acquire the semaphore if this value is 1. Otherwise, if thread returned by waitlist handler, kernel waitlist handler after elapsing the timeout from waitlist to the ready list, the thread has not succeeded to acquire the semaphore. So return by release will help us to determine will thread be able to get a semaphore or not when the RTOS put a thread to the waitlist. Okay, this is the responsibility of return by release. And after that, in waitlist handler in kernel.c in waitlist handler here, when you want to return a thread from waitlist to the ready list when its delay has elapsed, you must check if the thread has waited for a semaphore and inserted to waitlist by semaphoreGet after elapsing the timeout. You must delete thread from waitlist after finishing the timeout, and change this value semaphore waiting for in thread to null, because after timeout thread has not waited for semaphore anymore. So if a thread was inserted to waitlist by using of semaphoreGet, when this function semaphore waitlist wants to delete the thread from waitlist, first kernel waitlist handler must check if thread waiting for a semaphore, this function must delete the thread from semaphore waitlist and change this value to null. Okay, and in this way and in this situation, thread 1 will not be able to acquire the semaphore, okay, because until to the end of timeout no other thread releases the semaphore. Okay, this was the implementation of semaphore. Let's see an example. Now consider this example. I have two threads with priority normal, thread 1 and thread 2, and thread 3 priority is higher priority than other threads. I have a semaphore, created semaphore by semaphore create new. Max count of semaphore is 2, but initial count is 0. Okay, after creating the semaphore, the count of semaphore will be 0. If you run this example, because thread 3 has higher priority, operating system jump to this line. Now in this line I want to get the semaphore for thread 3, but the count of semaphore is 0. Okay, let's jump to this line. First jump to this line. Now thread 3 wants to get the semaphore, but the count is 0. So RTOS will put thread 1 to the wait list for 100 milliseconds. And if I put another breakpoint here and run semaphoreGet, jump to thread function 1 with priority normal, because thread 3 has been inserted to the waitlist. Okay, now if I release the semaphore 1 by thread 1 immediately thread jump to thread 1 action 3. Okay, here. If before finishing the timeout another thread releases the semaphore, and in semaphore waitlist thread 1 for example, or for example thread 3, okay, was most prior thread, thread 3 will be able to get the semaphore. If I run semaphore release, immediately the OS jump here and return value is okay. Okay, return value is okay. Return value is okay. Okay, but let's do change the example. Let's do comment this line. Comment this line. And another time run the example. Okay, another time thread 3 has the highest priority between other threads. RTOS jump to thread 3. Another time, if I get the semaphore because the count is 0, RTOS put thread 3 to the wait list, okay, and jump to thread 1. Okay, but at this time no other thread released this semaphore. No other thread released the semaphore because I've commented here. At this time thread 3 will not be able to acquire to the semaphore, and after 100 milliseconds thread returned by waitlist handler to the ready list. Okay, now if I delete this breakpoint and run the code, after 100 milliseconds source kernel, let's see, after 100 milliseconds, okay, 100 ticks, okay, thread 3 returned to the waitlist, returned to the ready list, but return value is timeout. Okay, so here was implementation of semaphore, and now you can use this locking mechanism or signaling mechanism to prevent conflicts in your code. Okay, so thank you very much to see me, and see you soon in the next part. Thank you very much.